In this class, we are deriving a formula for the time dilation effect and a formula for the length contraction effect. As we will see, to an observer at rest with respect to the clock, the time interval is always the shortest, whilst to an observer at rest with respect to the distance, the length is always the largest. A quick recap of the previous class. The evidences from binary star systems show that c, namely the speed of light, is independent of the motion of the source. In 1887, Michelson and Morley made a famous experiment where they demonstrated that c is always independent of the motion of the observer. Therefore, Einstein formulated his postulates of relativity, which say that no frame absolutely at rest exists, and as a consequence, non-local simultaneity is a concept relative to the experimenter. Let us study the origins of the time dilation effect. As we have seen, extended time is measured determining the simultaneity of events by means of a signal, which in vacuum can only be a light signal or a radio signal. Now, since every frame of reference has its own system of defining simultaneity, it must have its own unique measure of time too. Therefore, if we accept the postulate of the invariance of the speed of light, which has as a consequence the fact that every system has its own system of defining simultaneity, we have to accept as a consequence the idea that time is relative to every reference frame and not absolute. To state this differently, since c, which is a ratio between space and time, is an absolute value, the numerator, space, and the denominator, time, are no more absolute quantities. Every clock must agree in one frame of reference. Tutti gli orologi di uno stesso sistema di riferimento devono segnare il tempo in modo uguale. Si sta parlando ovviamente di orologi regolarmente funzionanti. Se infatti vi fosse disaccordo, potremmo attribuire questo disaccordo al movimento complessivo del sistema di riferimento ed utilizzarlo per rivelare anche il moto rettilineo a velocità costante, cosa espressamente vietata dal principio di relatività di Einstein. Abbiamo quindi la libertà di scegliere l'orologio che vogliamo. Ci serviremo di un particolarissimo tipo di orologio, un orologio a impulso di luce. Let's consider a light clock in which a pulse of light bounces back and forth between two mirrors, and it takes the light a time interval delta t0 to travel from the first mirror to the second mirror. Since light always travels at speed c, c by delta t0 is the distance between the two mirrors. Of course, this distance is a vertical line from the viewpoint of an observer at rest with the clock. First pulse, second pulse, third pulse, and so forth. But seen from the ground, light follows a longer path at the same speed c. Thus, it takes light a longer time interval. We will denote it by delta t, which is greater than delta t0. And the reason for this longer path is that when an observer standing still on the ground watches the clock moving toward his right at a speed v, from the instant when the light starts from the first mirror, the second mirror has moved toward its right, so that light actually follows a diagonal path like this one. And since the speed of light is always c, it takes light a longer time interval delta t to travel this longer path at the same speed c. Now, let us consider this right triangle, where the first cathetus is this one, whose length is the time it takes for the light to go from the first mirror to the second mirror, multiplied by the speed at which the apparatus is moving toward the right. And the other cathetus is the time delta t0 it takes the light to go from the first to the second mirror in the reference frame we have studied first, times the speed c, and the hypotenuse is the actual path of the light as seen from an observer at rest with the ground with respect to whom the clock is moving toward the right. Now, in a right triangle, the Pythagorean theorem holds, so that we have c times delta t squared minus v times delta t squared, this hypotenuse squared minus this cathetus squared, equals the other cathetus squared. We are now ready to do some calculations. We can factor out delta t squared over here and over here, so that we are left with a c squared minus v squared in brackets. We can now solve with respect to delta t squared, and we get a fraction, and in this fraction we divide the numerator and the denominator by c squared, so that you are left with a delta t0 squared at the numerator and with a factor of 1 over here minus another fraction of v squared over c squared. Now we can take the square root on both sides, and we get an expression for delta t, which is equal to 1 over the square root of 1 minus v squared over c squared times delta t0. And if we denote this fraction over here with gamma, we get gamma times delta t0. Now, gamma is a factor greater than 1, since its denominator is less than 1, because it is 1 minus a positive quantity, which is v squared over c squared, always less than 1. So we are multiplying the time with respect to an observer at rest with the clock by a factor greater than 1, and this is the time dilation effect, che in italiano viene tradotto con la dilatazione dei tempi. Let us see what is that physicists call the proper time, che in italiano si traduce con il tempo proprio. As we have seen, an experimenter with respect to whom the clock is moving will always measure a time interval delta t longer by a factor of gamma with respect to the corresponding time interval delta t0 measured by an experimenter at rest with the clock. We call delta t0 the proper time. In this table we have the gamma factor as a function of the ratio v over c that we have at the denominator here, As you can see, gamma is not much greater than 1 until v remains under the 90% of the light speed, and only when the ratio reaches values like 0.9998 we have a gamma factor of 50, namely delta t is 50 times longer than delta t0, and we have a gamma factor as big as 223 only when the ratio v over c is equal to point and then 5 nines to the right of the decimal point. This is the behavior of the gamma factor as a function of the speed. As you can see, it remains close to 1 and it gets steeper and steeper as you get closer and closer to the speed of light. And this behavior is the reason why we do not experience the time dilation effect every day, because everyday speed are too low with respect to this behavior to produce a considerable effect of time dilation like the one we have over here for values of this ratio as large as 99.9% of the light speed. The proper time is always the shorter one, shorter than any corresponding interval measured by an experimenter who is not at rest with the clock. When you consider a clock on board an airplane and two experimenters, one on board the airplane and one on the ground, the experimenter on the ground is not measuring the proper time, since he is reading on a clock in motion with respect to him. As a result, he sees the two events that define the interval happening, one here and the second one here, even if for the observer on board the airplane they happen at the same location. Of course, also the experimenter on the ground has his own proper time, measured on clocks at rest in his reference frame. And from the airplane's viewpoint, these clocks are seen to run slower. Do not forget that only a relative difference in experiment is allowed. If the observer on the ground said that the clock on the airplane is running slower, and the observer on the airplane said that the clock on the ground is running faster, that would be an absolute difference in disagreement with the relativity principle. Quindi, per quanto strano possa sembrare, ogni osservatore vede l'altro orologio nel riferimento in moto rispetto a lui andare più lento. One of the most beautiful evidences we have for the time dilation effect is the Muon Experiment, l'esperimento dei muoni. Muons are massive particles created in the high atmospheres from 10 to 30 kilometers above the Earth. Imagine 1 million muons are created over here. How many of them will reach the sea level? Muons are unstable particles. This means that at rest in a laboratory they decay into other particles after a very short mean life of only 2.2 microseconds, namely 2.2 millionths of a second. When they are created in the high atmosphere, they travel close to the speed of light. But even at this very fast speed, in the entire duration of their lifetime, they could travel only a very short distance of c times 2.2 microseconds, which gives a distance of only 620 meters. Therefore, we would expect to observe no muon at all here at the sea level, since they would die here after having traveled the short distance of 620 meters. In spite of these, we observe a high density of muons at the sea level, and the reason is that they are moving very fast, and this means that their clock goes more slowly. In our reference frame on the Earth, we have to multiply their time interval delta t0 by a very high gamma factor, and we get the corresponding time interval delta t, which is enough longer for them to travel a distance as large as 10 kilometers. The second important relativistic effect is length contraction, la contrazione delle lunghezze. Measuring the length of a moving object is a complex task because we cannot hold a meter stick against the object. If one wants to measure the length of a moving road, he cannot hold a meter stick against the road because the road is racing past. Therefore, we have to follow a different procedure, which consists in locating both the ends of the road at the same time. But, as we know, simultaneity depends on the frame of reference. Therefore, length too will depend on the frame of reference. As we will see, there's a length contraction effect. We can now derive an expression for the length dependence on the reference frame. Consider a road on board an airplane. From the viewpoint of an observer on the airplane, a pulse of light travels the road's length L0 in a proper time interval delta t0. Therefore, he measures the light speed to be c equals L0 over delta t0. But, according to the relativity principle, an observer on the ground must agree on the result of this experiment. Namely, he must agree on the measure of the light speed to be c on board the airplane. But from his viewpoint, the clock on the airplane runs slower by a factor of gamma, so that we have delta t equals to gamma times delta t0. Ora, l'unica possibilità per l'osservatore a terra di essere d'accordo sulla misura di c fatta a bordo dell'aereo è che, vedendo il tempo trascorso minore perché l'orologio va più lento, anche la lunghezza attraversata deve essere più corta nel suo giudizio. Therefore, he can agree on the light speed measure to be c only if he also judges the length of the road shorter by the same factor. Therefore, the length dependence on the reference frame is L equals to L0 over gamma, where L is the length measured by an observer on the ground and L0 is the length measured by an observer on board the airplane. The length contraction effect can explain the muon's survival down to the sea level as seen from the particle's viewpoint. As we know, muons are created at an altitude of 30 kilometers and, as seen from an observer who is standing still on the ground, they travel in direction of the sea level at close to the speed of light. But in the muon's frame of reference, the Earth is approaching to them at close to the speed of light. Therefore, there is a length contraction effect that changes the distance between muons and the sea level from 30 kilometers to 620 meters. As a result, since the distance to the Earth is shrunk, it can be easily passed during their very short lifetime of 2.2 microseconds. To complete our analysis, we will now prove that there is no disagreement in synchronizations perpendicular to the direction of motion and, as a consequence, no differences in length measurements perpendicular to the direction of motion. Let's consider two frames of reference S and S' traveling along the common x-axis. In the instant when the two y-axes are overlapped, a signal is emitted from point M coincident with point M' in S'. Now, no matter how strange it may seem, to an experimenter in S', according to the postulates of relativity, light spreads out spherically from M' exactly in the same way as it does from M in frame S. Therefore, an experimenter in S' can use these light rays along the y' axis to synchronize two clocks located, one at a position A' over here and the second at a position B' over here at the same distance from M'. They are reached simultaneously by the light, but also to an observer in S. The two clocks are reached simultaneously by the light signal, since we have no reason why the perpendicularity of the two axes could be affected by the motion. Therefore, these two lengths are equal. So the experimenter in S agrees on clock synchronization because also to him the light arrives simultaneously in A' and B'. Therefore, if we place a rod parallel to the y-axis, it is possible to locate its ends at the same instant, both in S and in S', and no disagreement on the rod's length will appear between the two frames. Therefore, we have no length contraction effect along the direction perpendicular to the velocity. Quindi, tempo proprio e lunghezza propria, proper time and proper length. A proper time interval delta t0 is the one measured by an experimenter at rest with the clock, and it is the shortest value for that interval among those measured by any observer, and the corresponding relation is delta t equals gamma by delta t0. A proper length L0 is the one measured by an experimenter at rest with respect to the distance being measured, and it is the largest value for that distance among those measured by any observer, and the corresponding relation is L equals the proper length over the gamma factor. Il paradosso dei gemelli, the twins paradox. Imagine one day we will have a spaceship that can travel at a relativistic speed like 0.9998 c. Okay, we must admit that the possibility to have human passengers on board is almost science fiction, since reaching a relativistic speed requires an extremely long accelerated phase, and man cannot bear inertial forces much greater than the one associated with 1 g of acceleration. Nevertheless, we will ignore accelerations and make a conceptual experiment. Here it is, our spaceship. For a spaceship traveling at a constant speed of 0.9998 c, the corresponding gamma factor is 50. Suppose there are two twins with synchronized clocks. The first twin, starting a travel on board our spaceship, headed to Vega, a star 25 light years away in space as measured in the Earth reference. And the second one staying at home. Let us consider things from the traveling twin's viewpoint. In his reference frame, the start of his journey and the end of his journey take place at the same location, namely just outside the spaceship. Therefore, the duration of the trip he measures is the proper time delta t0. Indeed, as we have seen, the proper time is the time interval between two events as measured by an observer with respect to whom the two events take place at the same location, which is exactly the case for the twin on board the spaceship. But the length of the trip he measures is not the proper length L0 equals 25 light years, since he is not at rest with that distance. In his reference, the system Earth Vega is moving past him at a speed 0.9998 c. Therefore, he measures a shrunk value, un valore contratto, L equals L0 over gamma. If we measure time in years, L0 can be written as L0 equals c times 25 years. We can now evaluate the duration of the trip from the spaceship reference frame. Delta t0, the proper time, is the measured length over the measured speed. The measured length is not the proper length, but it is L0 over gamma, and the measured speed is v. The two twins must agree on the value of their relative speed v. Otherwise, there would be an absolute difference between them, and this is not possible according to Einstein's relativity principle. L0 is c times 25 years, if we measure times in years, over 50, which is the value of the gamma factor, over 0.9998 c. We cancel off our c and we get 0.5 years. So it takes only 6 months for the traveling twin to reach the star Vega. And what about the twin at home? At a speed of 0.9998 c, the time dilation factor is 50. So, to the twin at home, the spaceship takes to reach Vega an interval delta t, which is 50 times longer than the proper time interval delta t0 measured by the twin on board the spaceship. 50 by 0.5 gives 25 years. Now, let's consider the round trip to Vega and back to Earth. While for the twin at home, 25 plus 25 equals to 50 years have passed, for the twin on the spaceship, the entire duration has been of only 0.5 plus 0.5 equals to 1 year. Therefore, in the moment of their reunion, we will no more see a couple of identical twins, but an old man and a young man embracing each other. And there's nothing paradoxical, it is a simple consequence of Einstein's postulates. Il paradosso nasce quando qualcuno vuole scambiare il ruolo dei due gemelli e far dire al gemello della Terra che lui si è mosso e l'altro è rimasto fermo, quindi lui sarà ancora giovane e l'altro, quello sull'astronave, invecchiato. Ma la situazione non è simmetrica tra i due gemelli. The situation is not symmetrical between the twins. There is no doubt it is the twin on board to be measuring the proper time, since in his reference frame he sees the start and the end of the trip happen at the same place, namely just outside the spaceship. On the contrary, the twin on Earth sees the spaceship starting the trip on Earth and ending the trip on the star, so the time on his clock must be longer than the corresponding proper time. Capito? È il gemello in moto a misurare il tempo proprio, il gemello a bordo dell'astronave, perché nel suo riferimento i due eventi accadono nello stesso posto, mentre per il gemello sulla Terra i due eventi accadono in posizioni diverse e quindi non c'è dubbio che l'orologio del gemello a terra sarà quello che segnerà 50 anni. C'è poi da dire che tutto l'esperimento richiede delle fasi di accelerazione e decelerazione all'inizio e alla fine e quindi andrebbe trattato in maniera più propria nel contesto della relatività generale. Language of learning. You say right triangle, cathetus, cathety, hypotenuse, sides of a triangle. The sides of a right triangle are called cathety and hypotenuse. You say the Pythagorean theorem or the Pythagorean theorem. The Pythagorean theorem holds for a right triangle. The numbers to the right of the decimal point are said one figure at a time. 0.348 and not 0.348 or simply 0.348, 7.56. Larger refers to physical size, greater refers to value, but for time you use longer or shorter. The proper distance L0 is larger than L. The proper time is shorter than 3 seconds. 8 is greater than 7. Language of learning. You express a certain variable as a function of another variable. We express gamma as a function of B over C. You say consist in, which means how something works, or consist of, which means to be composed or made up of. The procedure consists in locating both the ends of the road. But my lunch consists of one sandwich and an apple. You say to change from something to something else. The length contraction effect changes the muon's distance to the ground from 10 kilometers to 620 meters. You say to spread out spherically from light spreads out spherically from M. Some more language of learning. A physical property can be affected by another. We had no reason why the perpendicularity of the axis could be affected by the motion. You say in the same way as it does. Light behaves in S prime exactly in the same way as it does in S. You say in motion along the x-axis. The S prime reference is in motion along the x-axis. You say to travel at a speed v at close to the speed of light at relativistic velocities. The reference frame is traveling at a speed v. Language of learning. You say to go back and forth, andare avanti e indietro. The twin goes back and forth between the Earth and Vega. You say to be at rest with something or with respect to something or to someone. Essere fermi rispetto a qualcuno o a qualcosa. The proper time is the time measured by an observer at rest with the clock. You say to travel a distance, to pass a distance, to traverse a length. Light travels the distance between A and B. You say with respect to whom something is moving. The observer with respect to whom the clock is moving is not measuring the proper time. Language of learning. Vocabulary. In disagreement with, contrariamente a. A particle's rest frame life, la vita di una particella a riposo. To overlap, sovrapporre, sovrapporsi. To shrink, shrank, shrunk. Restringersi. A straight line, una linea retta.